At an altitude of over 11,500 feet in the Himalayas, this narrow and hazardous route was the only connection between the Kashmir Valley and the Ladakh Plateau. A few hours of heavy snowfall were enough to erase the road from the transportation map for months at a time, cutting off Ladakh from the rest of the country. Supplies, fuel, and even troop movements depended on a fragile window of favorable weather. Today, instead of accepting seasonal isolation as an unavoidable reality, modern engineering has taken a far bolder approach, going straight through the mountain itself. The Zojila Tunnel is one of the most ambitious high-altitude infrastructure projects ever undertaken, stretching more than 8.7 miles beneath the Himalayas. This two-lane road tunnel was excavated deep below the infamous Zojila Pass to ensure year-round connectivity despite snowstorms, landslides, and extreme cold. Rather than relying on a route that disappears each winter, engineers set out to create a permanent, always-on corridor through one of the harshest environments on Earth. In today's video, join Mandarin explores how this tunnel was built and how engineers overcame extraordinary geological and environmental challenges to keep traffic moving regardless of the season. The Himalayas are defined by rugged terrain, unstable geology, and extreme climate conditions, making transportation heavily dependent on winding mountain roads that are both dangerous and unreliable. Zojila Pass, located at approximately 11,575 feet above sea level, is a prime example.
In today's video,
it connects two regions with dramatically different geography and climate, the lush Kashmir Valley and the cold, arid Ladakh Plateau. For decades, this pass served as a lifeline, enabling the movement of goods, fuel, civilians, and military forces. Yet it remained blocked by snow for 5 to 6 months every year, leaving Ladakh nearly isolated throughout winter. To eliminate this strategic bottleneck, India launched the Zojila Tunnel project, a Himalayan road tunnel running deep beneath the pass. With a total investment approaching $1 billion, the tunnel reduces travel time from nearly 3 hours to just 20 minutes. More importantly, it establishes uninterrupted, year-round connectivity to Ladakh. It is a strategic infrastructure asset that strengthens logistics, enhances national security, and reshapes the geopolitical balance along South Asia's northern frontier. Building such a tunnel at extreme altitude introduced challenges rarely encountered in conventional construction projects. At over 11,500 feet above sea level, winter temperatures frequently plunge below -4 degrees Fahrenheit, while fierce winds and heavy snowfall can isolate the site for months. Under these conditions, the first task was not drilling into the mountain, but creating an environment where people and machines could survive and operate safely. Supplemental oxygen supplies and on-site medical facilities dedicated to monitoring altitude-related health risks. Laborers worked in short, rotating shifts to allow their bodies time to acclimatize, rather than remaining continuously on site, as is common at low-altitude projects. Independent power generation systems were also installed to ensure uninterrupted electricity, since the regional grid at such altitude could not reliably support a project requiring round-the-clock operation. Unlike many modern tunnels in Europe or East Asia, where massive tunnel boring machines operate through relatively stable geology, the Zojila Tunnel passes through a young and highly unstable mountain system. The Himalayas is still rising due to the ongoing collision of tectonic plates, and geological conditions can change abruptly within short distances. Engineers encountered everything from solid, intact rock to heavily fractured zones, weak layered strata, weathered material, and areas saturated with groundwater. A single unexpected shift in rock strength or a sudden surge of water could trap the machine deep underground, halting the project indefinitely. Instead, engineers adopted a flexible drill and blast approach, allowing excavation to proceed in small, controlled increments. Each cycle began with drilling precisely calculated holes into the rock face based on detailed surveys and real-time observations. The holes were positioned to fracture the rock efficiently while preserving overall stability. Carefully measured explosives were then detonated in a rapid, millisecond delayed sequence to limit vibration and reduce stress on the surrounding rock mass. Following each blast, work paused while powerful ventilation systems cleared dust, fumes, and toxic gases from the tunnel. In the oxygen-deprived environment of high-altitude construction, air quality was a matter of survival. The blasted rock was removed, exposing a fresh tunnel face and preparing the surface for immediate stabilization. To accelerate progress, excavation advanced simultaneously from both ends of the tunnel, but a carefully calculated and safe rate given the Himalayan conditions. Every meter gained reflected a balance between speed, safety, and constant adaptation to changing geology. Time played a critical role in tunnel safety. Freshly excavated rock, if left unsupported, could fail due to vibrations or sudden increases in groundwater pressure. For this reason, stabilization followed almost immediately after each excavation cycle. Fast-setting shotcrete was sprayed. Steel rock bolts were drilled deep into the surrounding rock to bind fractured layers together, redistributing stress and forming a more stable composite structure. Groundwater posed an equally serious threat, allowing meltwater to seep continuously into the excavation, creating internal pressure that can crack concrete and weaken the structure over time. Seeping water was captured at the tunnel invert and channeled out through dedicated pipes. This approach ensured long-term durability under relentless freeze-thaw cycles. Once excavation and primary stabilization were complete, construction moved to forming the tunnel invert, the structural foundation that locks the tunnel's geometry and supports long-term loads. With the main structure secure, the project system designed to function reliably for decades. The entire tunnel was comprehensively waterproofed, followed by the installation of a lighting system capable of operating in cold, damp, and dusty conditions. High-capacity fans and automated controls that adjust airflow based on traffic and air quality. In emergencies such as fires or accidents, the system can rapidly reverse airflow to extract smoke and create safe evacuation corridors. And safety bays were installed at regular intervals, enabling rapid incident detection and response. La tunnel into a controlled internal environment, capable of operating independently of the brutal conditions outside. It represents a sustained effort to control an environment never meant to host modern infrastructure, from creating livable conditions for workers and managing oxygen poor air, to drilling, blasting, stabilizing, waterproofing, and installing advanced operational systems. Every step served a single purpose: turning a route once blocked by snow for months into a permanent year-round lifeline. If Zoji La Pass symbolizes the unforgiving challenges of the Himalayas, the Zoji La Tunnel is modern engineering's response. Instead of surrendering to isolation imposed by nature, humans chose to pass straight through the mountain itself. The project does not simply alter a transportation map, it redefines how infrastructure can be built in the world's most rugged terrain. And the Zoji La Tunnel is only one link in a much larger chain. As humanity continues to carve paths through high mountains, don't forget to subscribe to Talktella so you don't miss the world's most impressive engineering projects.